Using generic interfaces for persistence is great from a code reuse point of view. With just one simple interface, any entity can be persisted using a standard set of operations. If you're using aggregates, you can use generic constraints and a simple marker interface to ensure that only aggregate roots can be persisted using your interface. It can work really well.
But there are trade-offs. What if you have certain aggregates that should never be deleted, but your generic repository includes a delete method? Does it make sense to have operations defined in your domain model that should never be used? This is where you need to make a judgment call. Is the convenience of having a single, consistent way of dealing with persistence throughout your model more valuable than having only the necessary and appropriate persistence operations exposed? There's no one right answer. Pick what makes sense for your app, your model, and your team.
In our demo, partially for the sake of simplicity, we are using a single generic repository for all of our operations, even though, yes, this means there are operations on some aggregates that are never called and some that never should be called, for example, deleting the entire schedule.
If we didn't go that route, our model would need to include separate repository interfaces for each of the aggregates in our model, including schedule, doctor, room, client, and appointment type. Each would define only the operations that were actually needed by the application. For a larger model, this could result in quite a few interfaces and possibly implementations, but would provide a more pure representation of the domain model.
If you do choose to create a generic repository interface, that doesn't necessarily mean you'll implement it generically. You might only choose to create implementations for each aggregate root, which would comply with DDD recommendations. However, it can be convenient to create a generic repository of T implementation class that you can then use with any entity.
This is what we're using in our sample, both for the front desk app and for the clinic management app. In both cases, if you review the sample, you'll see there's very little persistence-specific code in either solution.
If you really like the code reuse you get from having a generic repository implementation, one way to keep it from allowing too much access to the internals of your aggregates would be to use a marker interface, perhaps one that simply extends the entity interface to identify your aggregate roots. Then, you could update your generic repository to require this interface, rather than working with any entity.
At that point, code that uses the repository won't be able to instantiate the generic repository with non-root entities. So we're able to use our repository to restrict access to non-root entities from clients of our model. Using marker interfaces to identify aggregate roots is one way you can enforce your design decisions in your model using the compiler, rather than relying on code reviews or other less effective practices.
Repository abstractions, especially generic ones, can sometimes get to be pretty large. Large interfaces violate the interface segregation principle, one of the solid principles that I cover in my Solid Principles for C# Developers course. One way to keep these interfaces smaller and more focused is to split them into read and write operations. This is related to the concept of Command Query Responsibility Segregation, or CQRS. Read operations are queries, write operations are commands. There are many benefits to leveraging CQRS that we don't have time to cover in this course, but one area where you may immediately benefit is with modifying behavior related to these kinds of operations. Queries often benefit from data caching, and it's very easy to add data caching to just the read operations.
Commands often benefit from being performed asynchronously using a queue, and having a separate interface for commands makes it easy to implement this behavior. These are just two ways you can quickly leverage splitting up your repository definitions between reads and writes. Of course, if you have a lot of different read methods, this can make it more and more difficult to implement custom caching logic, since every new method will also need to be added to the caching layer. Fortunately, this is easily solved by using the specification pattern. Steve is going to give you a guided tour of how data access and persistence are handled in the front desk application using repository abstractions. Because he's been fine-tuning versions of this demo application for many years, it's quite impressive, and he truly is the best guide for walking you through this implementation.
We'll start from the front end of the application, which is our Blazor client. Let's take a look at editing an appointment. Here's an appointment for Julie's dog, Samson. You can see that on the edit screen, in addition to showing the details for the appointment, it also provides us with a list of the doctors and appointment types. When we hit the drop-down list, we can see all of the different doctors who are available that we could schedule to work with this particular appointment. That's actually accomplished through a back-end API that's coming from a different project. Let's take a look at that. We'll start by examining the API using our Swagger endpoint. Looking at Swagger for doctor endpoints, you can see that there are two endpoints, one to get a specific doctor by ID, and another one that returns a list of doctors. We just saw the list of doctors in action. Let's go ahead and run it again from Swagger. Here you can see the resulting set of 3 doctors, just like we saw in the drop-down list. You'll find the code for this particular endpoint inside the frontdesk.api project. Within there, there's an endpoints folder with subfolders for each of the different types of entities that we expose API endpoints for. Inside of Doctor, you can see there's a get by ID and a list, and we're looking at the list endpoint here. When we define an endpoint, we simply inherit from base async endpoint and specify the request type, if any, and the response type, if any. We can also do dependency injection through the constructor, just as you would with a controller. Each endpoint has a single handle or handle async method, and this is where the actual work of the endpoint is done. You can see in this example that we are simply awaiting on the repository's list async method in order to get our list of doctors. Once we have the list, we map it to our DTO that we're going to actually return and pass that back as part of that response type. The response, as we just saw in Swagger, includes the doctors as JSON, as well as a count property that includes the total number of those doctors. Now let's look a little bit more closely at that repository. You can see in the dependency injection that's occurring in the constructor that we're depending on an iRead repository of doctor. But where is that defined? For that, we need to look at our shared kernel project. Inside the separate shared kernel project, which FrontDesk references as a NuGet package, you can see that we've defined an iRead repository of T interface. This inherits from iRead repository base of T, which is actually itself defined in another NuGet package, the Ardalis.specification type. The reason why we're creating our own interface here is so that we have complete control over it and we can add additional behavior. For example, in this case, we're adding a generic constraint. We've said that this particular interface will only work with types that have the iAggregateRoot interface attached to them or applied to them. Looking at that particular interface, you can see that there's nothing to it. It's simply a marker. It's a way that we tell the compiler that our intent for a particular class or entity is that it should be treated as an aggregate root. We use that marker to enforce our design and our encapsulation to make it so that we don't accidentally just load up a child entity out of an aggregate when instead we've made a design choice that we want to work with that entire aggregate as a unit. You can see that we've also implemented iRepository of T similarly. It also inherits from a type that comes from Ardalis.specification and also has the same iAggregateRoot restriction. Now let's return to our FrontDesk application and see how we implement this. First, we should look at the default infrastructure module. This is an AutoFac module that defines how we're going to wire up our abstractions with their implementations. And here you can see all the important bits of how we wire up EF repository to iRepository as well as iRead repository. But notice for the iRead repository, we're actually wiring up a different type, a cached repository. This acts as a decorator around the underlying EF repository and will provide additional caching logic. Inside of the cached repository, when we asked for a list of doctors, it actually checked the cache first, and then if it wasn't in the cache, it would go and fetch the result from the EF repository, which in turn would make the request to the database. We can see in this example here that the logging is showing us that we're actually hitting cached repository. And some of the times we're fetching the source data, and other times we're fetching the data from the cache. The actual EF repository that is also defined inside of frontdesk.infrastructure is shown here. And once more, you can see that there's not much to it. most of the behavior we're simply inheriting from the EF repository that exists in the ardalis.specification package. It's called repository base of T. However, when we inherited it, we were able to add additional constraints, and so you'll see here as well that we specify that this only works with iaggregate root. You can see the definition of the repository base of T in the ardalis.specification NuGet package, which is available on GitHub. The details of it are shown here. The list async method simply delegates to dbcontext.set of the appropriate T type, and then calls its toListAsync, passing along a cancellation token if one was provided. Now the last piece of the puzzle is our own appdb context. Inside of our appdb context, we define the DB sets that we're working with, and we also pass in some additional configuration. One thing to notice and take away from this example is how many places in our solution we have to reference appdb context or entity framework. It's almost nowhere in the entire codebase. The only place that we talk about it at all is inside of appdb context, EF repository, and some related folders such as configuration and migrations. Everywhere else, and especially in our domain model, we're completely persistence ignorant, relying only on abstractions that we've defined.